MAP4C 1.2 Investigating the Sine, Cosine, and Tangent of Obtuse Angles. An angle is measured counterclockwise from the x-axis. As you see here, this is the x-axis, and on the positive side is where we consider that terminal arm to start. So if we rotate counterclockwise from this position, you can see that we've named the quadrants 1, 2, 3, and 4. So we're going to apply these primary trigonometric ratios to angles that are obtuse, and obtuse angles are between 90 and 180 degrees. Acute angles are between 0 and 90 degrees. So the x and y axes split the Cartesian plane into 4 quadrants, as you see here, and we're going to see the behavior of the primary trigonometric ratios in each of these quadrants. So let's contrast an example with acute angle A and an obtuse angle A, which is in the second quadrant. So what are the coordinates of point P? Point P, if we count starting off with x and then y, 1, 2, 3, 4, 5, 6, 7, and y is 1, 2, 3, 4, 5, 6, 7, 8, 9. So the x and y coordinates of the point P is 7, 9, always in that format. Similarly, here on the x-axis it's positive in the right direction, negative in the left direction. So it's negative 1, 2, 3, 4, 5, 6, 7 left. So negative 7 for x, and 1, 2, 3, 4, 5, 6, 7, 8, 9. So negative 7, 9 is the position of that point P. So what is the length of the terminal arm R? If we look at this here, the terminal arm R is the hypotenuse of this triangle. So if we know the x and y coordinates, then we can use Pythagorean Theorem in order to determine the length of the terminal arm. So we'll substitute into this accordingly. A and B are both legs of the triangle, and the hypotenuse is C. So applying it to this situation, we have the x and y are 7 and 9, and instead of saying C, we'll use R so that it corresponds to our image. So we evaluate the exponents, add together each term, and take the square root to find out the length of our terminal arm is 11.4 units. Units because the values are not specified, or the scale of x. Next, for the obtuse case, we're still going to use Pythagorean Theorem because we have two sides of the triangle known, but the hypotenuse is unknown. So the only difference is that the x component is negative, and that's not going to affect our situation here. Our radius, or sorry, our terminal arm will always be a positive value. So that negative 7 is squared, and a negative number times itself will produce a positive product. So we'll solve in a similar manner and get the same result. So these are mirror images of one another. When we determine the measure of acute angle A, that means in this case the angle that it's making with the x-axis on the positive side. So we know that we have the opposite and the adjacent side, so we would be using the tan ratio. And in this case, the opposite is 9 and the adjacent is 7. As we said, it was opposite and adjacent from this reference angle. So using inverse trigonometric ratios, we can end up with the solution of 52 degrees. Now, determine the measure of acute angle A for this example. So what we can do is the following. If we know that the acute angle is 52 degrees, we can subtract that from 180 to find the remaining amount. So in order to find the corresponding angle on the outside, the obtuse angle, what we can do is the full length, or the full angle, 180 degrees, minus the related acute angle. Next, we're going to calculate primary trigonometric ratios for both the acute example on the left and the obtuse angle on the right. Let's start off with sine of A. Sine of A is equal to opposite over hypotenuse. So we now know the value of the hypotenuse. This was 9 and 11.4. Cos of A is adjacent over hypotenuse. We said that the adjacent is 7 and the hypotenuse is 11.4. Tan of A is opposite over adjacent. Opposite was 9, adjacent was 7. When we investigate the same primary trigonometric ratios with an obtuse angle, sine of A is opposite over hypotenuse. So in this case, we can think of it from this perspective here with the related acute angle on the inside. This is the obtuse angle, but this is referred to as the related acute angle. And the opposite over hypotenuse is positive 9, because it went up on the y-axis 9 units to get to that point, over the hypotenuse. So that's still 9 over 11.4. And it's evaluated as a decimal. Next, cos of A, the adjacent over hypotenuse, this is to the left on the x-axis. So this is a negative 7. And over the hypotenuse 11.4, that ends up being a negative value for cos. And then lastly, tan of A is equal to opposite over adjacent. The opposite is y, the adjacent is x. Notice that y is positive and x is negative. So the result, when you divide, is a negative value. So what can we take from this? The sine, cos, and tan in the first quadrant, or this quadrant, are always positive. But in the second quadrant, the only positive ratio was sine. The other ratios were negative.